All right, so today we're going to look at our other type of chi-square test. We actually have two more types of chi-square tests. Goodness of fit is a test that we use when we have just one variable, one categorical variable, and one like column of information. Okay? So we just had, like yesterday, the color distribution of M&Ms. So we're just trying to fit one variable, and we're trying to just do that one thing. Goodness of fit is the way to go. But oftentimes we get a two-way table of data. And that's where the test for homogeneity and independence, tests of homogeneity and independence come in. Now, I'm going to say this several times. The AP exam traditionally has not made you distinguish between a test of homogeneity and a test of independence. If you just say a chi-squared test, they've said that's sufficient. And that's always been the case up to this point. I don't know if they'll even put a chi-squared on there, or if not. But the problem is, in the past, if you just say chi-squared, you're okay. If you said chi-squared homogeneity and it was independence, you got marked down, or vice versa. But if you just said chi-squared without specifying homogeneity or independence, you got full credit. So my advice is always just say run a chi-squared test when you're naming your test. Don't use the terms homogeneity and independence. It is a little bit tricky to distinguish between the two. And the mechanics are exactly the same. So we're going to learn the two different tests today and tomorrow. The mechanics are going to be identical. The conditions are identical. I mean, everything's identical about the test. It's just the name because of the way the variables are set up. Okay? So if we're looking for a test of homogeneity, I mean, the key term here is homogeneous. We know that homogeneous means having a similar, they all have the same feature of some sort. Okay? Milton High School, for the most part, is very homogeneous when it comes to race. Right? I mean, we're 98% white people here. All right? It's not the world's greatest thing, but it's an example, and it's a true one. So again, the prefix homo, the same. So it's actually a generalization of a two-proportion z-test. And the test statistic is identical to the chi-squared statistic for goodness of fit. So we're still going to do observed minus expected squared divided by expected. So the same calculation. It's just that now instead of calculating that for every, or for just a column of information, we are going to have several cells in a two-way table. So the real interesting part is, how do we find the expected value? We have a table and we're trying to match a pattern. Finding expected values are pretty easy. I mean, for the Skittles, it's supposed to be an equal distribution, so you just took the total divided by the number of categories, and boom, there it was. You know, it could be something different where they assume it's 20% this and 50% that and 30% this. That's fine. You can still, finding the expected values is pretty straightforward. When we have a table, a two-way table, now finding the expected values can be a little trickier, but I'm going to show you the quick way of finding it. They don't teach you the formula, but it works. The question we're asking here is whether choices are the same among different groups. So basically what we're looking at is we're looking at one categorical variable, and we're looking at multiple groups to see if they're making the same choice. Okay? The expected counts are found directly from the data, and we have different degrees of freedom. So there are a couple things that are different. Our degrees of freedom can be a little different. Assumptions and conditions remain pretty much the same. Counted data condition, again, that's exactly the same as we had for goodness of fit. Randomization condition in 10%. As long as we don't want to generalize, we really don't have to check these conditions with this. As long as, if all we're doing is comparing if two different groups are distributing the same way, we aren't trying to generalize to a larger population, then randomness is no longer a necessary condition, because we're not trying to take this to a larger group. We're just seeing what goes on between these two specific groups. Same with 10% at this point. So that's different. Expected cell frequency count, again, all your expected cells must be at least 5, and there should be a little asterisk there. If one of them is like 4.5, go ahead, not a big deal. If you start seeing them down in the 3s and 2s, then we start having issues, or if more than one is down under 5, then we start having issues. Calculations are exactly the same. Observed minus expected squared divided by expected for every cell. We have to calculate the observed value for each cell, the expected value for each cell, and do that calculation. Since we have a two-way table, we have rows and columns. Our degrees of freedom is rows minus 1 times columns minus 1. Okay? So you actually have to take a look at our table, see how many rows, see how many columns, subtract 1 from each of those numbers. Now remember, don't include total rows in that, because a lot of times your two-way tables will have totals. They'll have the margins in there. Do not include the margins, only include the categories. And that's by degrees of freedom. And we'll find our p-value for our chi-squared statistic. Okay. If and when we reject the null hypothesis, it is always a good idea to look at the residuals. In other words, what is the observed minus expected? A residual is the square root. You take the observed minus expected divided by the expected value. In other words, it's the square root of the chi-squared, right? Because the chi-squared statistic is observed minus expected squared divided by expected. This is the square root. The difference is the residual is going to be positive or negative. So when we're talking about residuals for the cells, it's the square root of the chi-squared value for that cell. You don't need to do a new calculation, but you do have to pay attention to, am I above or below the expected value to know whether I'm going to have a positive or negative residual. So, and again, how do I know? It's always observed minus expected. I've been preaching that at you for so long. Hopefully observed minus expected is just drilled into your head at this point. Y bar minus mu, p hat minus p. Okay, same thing. Standardized residuals are the square roots of the components we calculated with a plus or minus sign. Yep. Standardized residuals give us a chance to think about the underlying patterns and to consider ways in which the distribution might not match what we hypothesize to be true. Because if we come up with a small p-value and says, okay, this is different, there is a difference between these two groups and how they impact this variable, well, it doesn't tell us what that difference is. It just tells us there's a difference. The only way we can start finding patterns and maybe see where the difference is by examining the residuals. Okay? So that's important as far as analysis of the data. Okay, Dick's Sporting Goods wants to compare the number of sales in thousands across 3 stores to see if they're the same last year. They look at 3 categories of sales: golf, footwear, and hunting supplies. The data is below. Is there evidence to suggest the number of sales may vary depending on store location? So we're really looking at, now here we're looking at their counts being counts of dollars. Okay, the one thing we're comparing one variable, dollars, of sales. Okay, we're looking at 3 different categories in 3 different stores. Is there a difference in the pattern of how things are going? So what we're going to need to do, I'm not sure if my next slide has the margins in it. No. Okay, it just has the same thing. Is we're going to have to look at this. And first thing is, how do I find the expected values? Well, what we're going to need to do is we're going to need to calculate our row and column totals. Okay, so we're going to have to add a totals. Have to add our margins in here. And calculate those totals. So golf, I'm going to have to take 12.5 plus 16.4. Whoa, let's try that again. 12.5 plus 16.4 plus 21.8. That's a 50.7. I'm going to make that small. For footwear, it is 17.7, 17.9, 30.9. I'm just going to do this in my calculator. I'm too lazy today. You ever have one of those days? I know I could do it in my head, but I really don't want to. I don't trust myself today. 54.9. If I add those up, plus 30.9, I get 136.5. In the columns, that's going to give me 30, 31.3, 31.6, 39.6. That didn't work. Helps if I push the right button. 16.4 plus 9.4 plus 17.9. 43.7. And let's see now, that's 34, 35, 53.2. I'm going to sum across my bottom to make sure that those numbers add up. $136.5, yep. So they both add up to 136.5, so I'm pretty confident in my numbers that I've added them correctly. That's a good error check to do. Make sure your row and column totals add up. To find my expected values, here's the trick. For each cell, you take the row total times the column total divided by the grand total. Okay? So 50.7 times 39.6 divided by 136.5. I have an expected value of 14.7 right there. And we do that for every single cell. So the expected value for Madison West would be 50, golf would be 50.7 times 43.7 divided by 136.5. 16.23. Okay? And this is how we find our expected values. Yes, it's kind of a tedious process, but it does work. And I could go into the theory behind it and everything else, and we could talk about, well, this is, you're going to find the proportion of this versus the proportion of that. You know what? Let's just make it a simple formula. Row total times column total divided by grand total. I think that's coming from the construction. Okay. No, it's coming from Spanish. Because of course we have funny noises coming from Spanish. You always get. That's fine.
Please excuse this interruption. For any students in the building that have not exchanged their laptops as of yet, please go to the library now. Again, if you have not exchanged your your laptop, please head to the library.
If you haven't exchanged your library, I haven't exchanged my library. I have to go. Have you exchanged your library?
No, it was really hard to. It's not exactly portable, so I've been struggling to bring it portable.
Well, come on now.
I know.
I was thinking, what would they say? I mean, I would be so mad if they said, guess what, guys, we're going home. It's like, what?
I was here for me too.
And guess, but staff, you get to stay here and teach your virtual lessons from here all morning. It's like, that's kind of what I'm expecting. What's the difference now? I'm up, I got dressed, I had to take a shower and everything. Pay attention to personal hygiene for the day. Once you've done that, you've done all that work, you might as well be out of the house, right?
Yeah.
I mean, the cats don't care if I shower. So, Okay, and then again, so to find the chi-squared statistic for each cell, we'll just do it for a couple example cells here. I take the 12.5 minus 14.7, which is obviously negative 2.5. And square that, so 2.5 squared divided by expected. And I get a chi-squared value for that particular cell of 0.4251. And if we're doing this manually, what we do is leave lots of spaces in our cells. And we put in our observed, our expected, our chi-squared value. And we can also put our residual in there, which would be the square root of 0.4251. But it'd be negative. So my residual is negative 0.6520. Okay, the red is my chi-squared. And yes, the chi kind of looks like an X. All right? And we basically, if we're doing this manually, that's what we do for each cell. Yeah, good times. You're saying, do we really have to do that manually? Well, sometimes yes, usually not. Because what do? We do have to calculate our expected values manually, all right? But what we normally will do is we do this using our calculators, using the matrix function. Now this is going to be new. Okay. The matrix button for your calculator is the x to the negative 1 power. So second function alpha, math, x to the negative 1. So second function x to the negative 1 going down the left side of your calculator. I'm holding it up there, it's right about there. Second function there. And what you're going to do is you can name your matrices, but you don't want to change their names, it's fine. And then you want to edit your matrices. So you go over to edit. And first you have to tell the dimensions of the matrix. Obviously this is a 3 by 3 matrix, right? So tell it's 3 by 3. And it gives you a nice little matrix on the screen. And you just start putting your numbers in where they belong. 12.5, 16.4. It's like you're making a list, you're just doing it in the chart. Oops. Make sure you get the right numbers in there because they put bad data in, obviously you're going to get bad results. Okay? So that's your first matrix. That's the raw scores. The second matrix you're going to have to create as a residual. So you do actually have to go through and calculate the residuals for each cell. So to save a little time, what we're going to do is I'm going to give everybody a cell to calculate because we have 7 cells left and 7 people. So Ellie Waukesha Golf. Allie can take Janesville Footwear. Abby, Madison West Footwear. Grant, Madison West or Waukesha Footwear. Nick F, Janesville Hunting. Nick N, West Hunting. And who did Taylor? You get Waukesha Hunting. So calculate your residual, row total times column total, divided by grand total. And then tell me what you're doing, because I don't remember who I gave what. So who had, well, I'll just call it this way. Who had Waukesha Golf? Okay. What did you get for Waukesha Golf? For the expected value, yes. 14.7. Okay. Who had Janesville footwear? You did, okay, Helen? 8.96. We'll go to 9.0. Okay, we'll go to one decimal place here. West footwear. Who had that? Well, I might not have my volume on. Say it again, Abby.
9.9.
9.9. Waukesha footwear. That was Grant, right?
I'm still kind of confused what we're doing with our calculator here.
Okay, we're just calculating the expected value. So I'm going to find Waukesha footwear, I'm going to take my row total for that, times my column total, or I just did those backwards, but that's okay. Row total times column total divided by grand total. Oh, did you?
Yes, it's 19.7.
No, it's right.
Uh, 19.54.
It seems high. Let me check that. $30.9 times 53.2 divided by 136.5. I got 12.0. Try that again. Try 30.9 times 53.2 divided by 136.5.
Oh yeah, I got it now.
Okay.
I just did the wrong number for the last one.
Yep, that'll do it. All right, how about hunting for Janesville?
I got 23.0.
West hunting. Nick, you got that?
West Hunting?
Other Nick.
Oh, okay. Sorry.
There are two Nicks here, it's very clear. Nick Niemeyer, you got that number for me? Do you have any audio on? Maybe I need to chat at him. Taylor, do you have your number?
I got 21.4.
21.4. Sorry.
Sorry, what?
Do you have the number for me? The Madison West hunting?
The number of what?
The expected value for Madison West hunting.
No.
Can you get that for us, please? Okay, apparently Nick isn't going to do that, so. So 43.7 times 59.4, 54.9, sorry, divided by 136.5. I get 17.6. All right, so now what we're going to do is we're going to go back to our matrix menu. And we're going to put in matrix B. Make it 3 by 3. Whoops. Got to hit the right buttons. There we go. Edit. Edit it. There we go. And put our expected values in there. All right, so we've got all our expected values now. And now we can go to, oh wait, I still hear clicking going on. Now we go to our stat menu, tests, and faster to go up than down, but C, chi-squared test. Your observed values we have in A, our expected values are in B, and we just go to calculate. What? Error domain? Interesting. That shouldn't be happening. Value entered is not allowed in the function or command. Example. That's interesting. Not sure why that's happening. Shouldn't be happening. Let me double check to make sure my matrices are still there. A is 3 by 3. Edit A, it's the right matrix. B, I've got the right matrix. Well, this is a little confusing. Not sure why that's happening. They're the same dimensions. I know they have to be the same dimensions. They're not the same dimensions, it wouldn't be work. All right, I'm going to have to figure out why it's giving us errors right now. But that's normally how we would do that. And it'll spit out all the information we need, and then we can continue our analysis from there. So let me take a few minutes to go ahead and see if I can figure out why it's giving us an error right now. And in the meantime, sit tight, and you can actually probably get started on your assignments. It'd just be nice to make sure the calculator can do this, so you don't have to calculate your chi-squared statistics manually, because that's kind of a pain. So stand by, and we will get back in there.